Right. So today, in this session, firstly, we need to do a quick revision on uh, distributed databases and do the past papers. Okay. Right. So let's do a quick revision. Right. So the distributed database management systems are used when you want to distribute your database among different clouds or different machines in the internet, but those are not close. Right? Those are not close by machines, maybe in different countries, different places, and so on. Okay, not in the same data center, two different machines. Okay. Uh, so remember, we can distribute in two different way. One is distribute at database level. The other one is you distribute at application level. So then we use service-oriented architecture, microservices, and so on. But this subject is distributing the database. Right? Distributing the database. Maybe you have the local systems as well connecting to that local database. Okay, right. So therefore, those are two different things. Okay. Uh, so you can have distributed servers with centralized database, distributed servers with distributed database. So what we are interested in is the second one. Okay, second one. Right. So what are the advantages? There are both advantages and disadvantages. Disadvantages are obviously the additional complexity, but the disadvantages are the scalability because your database is now distributed, right? And some tables will be in only one place closer to their user base, right? And better performance because maybe your database is not packed with all the data. Particular uh, branch is having only the relevant data. Sometimes it can be less performance also because maybe you need to get data from other databases. It depends on the way you use it. Okay. And better availability. Obviously, your database is multiple copies are available in different sites. And of course, the agility, right, where you have a lot of flexibility. So certain nodes you have common data, certain nodes you have common data for specific data for that site, and so on. So performance, in a way, it can improve it, and also sometimes it can decrease it. But if you use it in the proper context, overall, most probably it will improve the performance. Okay, right? Better availability because of the redundancy, and also when one node is down, still the other node will provide you the data, okay? And so on. Right. So when it comes to scalability, so there are two types of scalability: vertical scalability and horizontal scalability. So horizontal scalability means you can increase the number of nodes horizontally, right? So that means basically you have more and more nodes. So you can add another node. So then some machines are now connected here. They used to connect here, right? So that is scalability. When you need more and more, when we have more and more users, we can add more and more nodes. But vertical scalability is you increase the capacity of the individual node, right? Better memory, better storage, and so on, right? So then few more concepts we learn. Uh, partition tolerance. Okay. So that means when there's a network failure in, okay, uh, so then we can make it into partition into subgroups and so on. Okay. So that the idea is system must be must be having high availability. When one node set of nodes are down, still others must operate, and also those served by that failed nodes must be served by another node. Okay. But in order to do that, we need to manage, right? We need to manage the partition. Okay. So that means when there's a network failure in, okay, so then we can make it into subgroups and so on. Okay. So that the idea is system must be having high availability. When one node set of nodes are down, still others must operate, and also those served by that failed nodes must be served by another node. Okay. But in order to do that, we need to manage right? Separating it to sub nodes, sub networks, and so on. Otherwise, when one failure will make everything down. Okay, right. Right. So types of distributed databases. So the homogeneous versus heterogeneous. Homogeneous means in different sites you have the same database in the system. If it is Oracle, everywhere Oracle. If it is Microsoft SQL, everywhere you have Microsoft SQL. So that is relatively easy to manage because technology-wise it's compatible. Heterogeneous system means different sites you have different DBMSs. Maybe one site Oracle, other site MS SQL. So that is very challenging uh, because you need to make those compatible. Okay, sometimes through another layer. Okay, right. So the next one is autonomy. Autonomy means independence or freedom. Okay, uh, so we can identify different levels of.
So I have a doubt.
Yes.
Why do we need to choose the heterogeneous database system?
Sometimes what happens is now if someone asks why there are still some systems which use very old technologies. Sometimes these companies or these organizations have locked to those old systems. Maybe they are running an old system in that site with old technology. Maybe it only support Microsoft SQL. Now that branch or that site cannot easily migrate away from Microsoft SQL, but maybe other branches or other main site they have transferred to Oracle. Right? So that kind of situation can happen. So sometimes they are those systems, so those organizations, branches, they have lock into the particular technology, right? So we call it vendor locking. So that is because these systems may have been developed about 10, 20, 30 years ago. Still, there are some banking systems and so on which use very old technologies in reality, right? In reality, right? Sometimes we get surprised why they are using those kind of things because maybe it's in some other countries, maybe that branch is in Russia, right? That branch is in China, that branch is in North Korea, right? Maybe African country. So then there are so many issues. Okay. Likewise. Okay. So these are rare, but can happen. Right? So therefore, yes, heterogeneous systems can exist. Okay. Uh, right. So the autonomy we can subdivide or we can look at it as design autonomy. That means we have the better freedom when it comes to designing. Uh, Communication autonomy. That means we can use different communication protocols for communication between different nodes. Okay. And execution autonomy. That is the users or the user sessions can operate or execute in a more free manner. Okay. So these are more conceptual things. Okay. Uh, so then another classification is, so these are the aspects anyway. The real classification based on autonomy is a pure distributed database. So that means we have multiple sites, but there's a global schema. So every user see the same schema, though we have multiple sites. So that is pure distributed data. That is the ultimate objective, right? But there can be uh, multi-database systems where the full local autonomy is there, but maybe you lack global schema, right? So that means full local autonomy is there. They can connect and develop their own way do things, but there's no global schema, right? Doesn't have a global schema. So that is the other extreme. Okay? So here no local autonomy, but one global schema. So that is one extreme. This is the other extreme. So this is sort of a best of both. Okay, best of both. You have global view, that is, you have the global schema. Okay, but at the same time, there's a bit of uh, locus autonomy as well. That is called federated. Federated is something like federalism, bit of both. Okay. Right. So then allocations. Allocation means how do you distribute your data? How do we distribute the data? Okay, into nodes. So again, it depends on performance requirements, availability goals, type of transactions you are going to execute frequently, and frequency. Okay. Uh, right. So what are the different type of allocations? You can go for centralized allocation. So that means all the data in one side. So that is not actually distributed database. That is centralized database. Okay. So then you can partition allocation. So that means you partition your data into separate sites. Some data inside text, some data inside Y, some other data inside Z. That is you partition your data. Right. So at the same time, you can have replications. So that means some data is common in multiple sites. Maybe Z data set is in or those tables and data in both X, Y, and Z or all the sites or some sites. So that is replication, right? So we can partition, we can replicate, or you can use both. Bit of partition, bit of replication. Actually, in reality, we use both. Of course, if you use this approach, it is not distributed database. Okay. Right. So again, there are pros and cons. Right. For example, uh, when we partition it, complex queries need to take data from one side to the other side and so on. That make trans query processing complicated. Sometimes it will make it slower, right? So there can be synchronization overhead because same data is in multiple site means uh, when this is updated, we need to update that also. Otherwise, it's inconsistent, right? So uh, that is when you have replication, okay, replication, uh, and of course the dynamic workload because we need to decide how the partitions is done, frequencies, and so on. Okay. Right. So then the fragmentation. So fragmentation is very much related to the allocations. Okay. Uh, so fragmentation is pretty much related to uh, replication or partitioning. Okay. So that is why I say partition is also fragmented. Right. So how do you divide your data? So basically, there are two approaches: uh, table level distribution and record level distribution. Okay. So that means you decide table X go to this side, table Y go to that side. Okay, maybe EZ side you have common table and maybe new table. But we are more interested in record level fragmentation. Okay, record level fragmentation. That means some records in exact same table in both X and Y, but some records in X, some other records in Y. So that is record level or column levels. Some columns in X, some columns in Y, but there should be common columns also so that you can join those. Okay. Right. So therefore, it results in three type of fragmentation. This is record level, horizontal, vertical, and mixed. Okay, horizontal, vertical, and mixed. So what is mean by horizontal fragmentation? So you have the same table in multiple sites, right? But some records go into site text table, some other records go into site wide table. Maybe these are two branches, X and Y. Branch X employs the record side, branch X table. Branch Y employees data in or customers data in Y table. Same table, but different records go into different uh, nodes. So that is called horizontal fragmentation because this branch may not need details of customers of this branch. Okay, right. And also when your branch customers are in your local table, it's faster to access, faster query processing, right? Rather than taking from a common place. Then there's a network communication. Okay. So that is called horizontal fragmentation. So some reports go there, some reports go there, different sites. So then you need it's this is how you explain it, sigma, right? Sigma is uh, based on the where condition, right? Where condition. So department sales in sales sites, the department marketing in marketing site, maybe they are in two different locations, right? So that is selection, not projection. So so uh, horizontal fragmentation is done by selection or sigma. Okay. Vertical fragmentation is basically projection. Some fields go into site X, some other fields go into site Y, but there must be at least one common field that is your foreign the primary key. Okay, so that at any time we can join these and get the full column set. Okay, so that is vertical fragmentation. Maybe columns related to account department in accounting table, account department side. Columns related to HR department in HR department sites and something like that. Okay, vertical fragmentation. Okay, but there must be a common field so that we can get the total picture. So how do we explain the partition using phi? Because this is projection, not selection. Okay, so then you can have mixed fragmentation. That is where you use both horizontal fragmentation and vertical fragmentation together. Okay, so that is called mixed fragmentation. So you can see here, so this is vertical fragmentation. So all the records, only two fields are here, right? So other two fields are in these two sides. Therefore, it's overall vertical, but at the same time, there's horizontal fragmentation. Some records go into the site sales, some records go into the site marketing. Okay, so that is first vertical, and then this vertical fragment is further horizontal fragmented. Okay, so that is called, uh, but here you need to have the primary key, and here you must have a overlapping. Right, so that is fragmentation. So remember, we are interested in replication also for better availability, sometimes better performance, uh, right? Availability and even performance, right? Because you have in your local site duplicated data, then you don't need to go to another site. Availability, because if one site is down, maybe you can get it from the other side because it's duplicated. Okay. Right. So when it comes to replication, we have three strategies: full replication, no replication, partial replication. So the name itself says full replication means so the same copy is in multiple places, entire database. Okay, entire database at every node. Okay, so that is full replication. Of course, the other extreme is no replication. So that means you only do fragmentation, you don't do any replication. So that means you don't get that advantage of availability performance. But at the same time, it make it simple as well. Okay. Most of the time, what we do is mixture of those. Some data is replicated, some data is not replicated. So that is the reality. Okay. So that is called partial replication. Only some fragments or tables of the database are replicated in selected sites. So that means if you do it in a sensible manner, it will overall improve your performance at the same time without unnecessary overhead of synchronization. right? Because you don't need to synchronize everything like in full replication. At the same time, your local site, there are data that you frequently need or what is more related to you. So that is partial replication. Okay? Because some data may be related to multiple sites. So those things are replicated. Okay. So you need to balance out and look at the requirements and decide to which level you are going to replicate, to which level, which strategy, in which strategy you are going to do fragment. Right. So then the distribution modes and distribution modes. So we can consider three modes. What are those? A single server, a sharding, and master slave. Okay. Uh, Obvious single server is not distribution. So that means it's a centralized database, right? So that is not distributed database. That is good if you have only limited number of usages and so on, right? So the performance is not your ultimate objective, right? So then single server actually anyway that is not distributed database. Okay. So sharding is basically you physically splitting data into several parts. Now this concept is actually looking at the same thing in different point of view. Okay, right. So that means basically this is another way of looking at partitioning. Sorry, fragmentation. Okay, physically splitting your data into different parts or different sites. Okay.
Sir,
Yes,
is that sharding is fragmentation plus replication?
uh, not replication, right? It's more related to fragmentation, right? Because it's you distribute. Uh, yeah, I'm also not 100% sure about that. It's talk more about the physically you splitting, but at the end, logical splitting also you need to get into a physical level. Uh, yeah, it's a good question, but I also have a little bit of a doubt exactly because I have seen these two words they use interchangeably. Okay, interchangeably. Uh, so shall we ask ChatGPT and double check that also? Okay, let's take this class in brief because we don't need a lot of details. Split data table into smaller pieces, right? So there is we know replication, copy of the same data. Uh, Split data across multiple servers. So each server store different data. Special case, so yeah, you can see it's a special case of fragmentation, right? Rather than uh, replication, right? A special case of horizontal fragmentation across servers. Server 1 uses A to M, server 2 uses N to Z. And you can see that still this is, right, it's a special case of fragmentation. So then someone will ask, why do we need another name for that? Right? Yeah, still you can see the ChatGPT's answer is also not very conclusive, right? Of course, now if you want, you can challenge, okay, ChatGPT. Uh, yeah, how data is, this is how data is divided. This is how data is divided across servers. Yeah, at the end, it's across servers, right?
So I think fragmentation can be done in the same database or different database, but
But
sharding is a
if it is
fragment.
different, same database, that is not our focus, right? Our focus. That means you have two tables for two fragments, say something like that. So rather than having say
Yes.
one employee table in the same database, you have two tables, say HR department employees and say finance department employees. But then that is not something a theory related to distributed databases, right? It says how versus across servers. Yeah, if this is across servers, this must be same server also included, right? Okay, we can challenge ChatGPT also, right? So you can say, is fragmentation same as give an practical examples? Show the difference. So they say no, these are two different things. Look how data is split. Yeah, it says logical again. Right, let's say practical example, student ID, name, department, year, fragmentation. Uh, so student CS, students E, student business. We don't care where they are stored, right? It doesn't say that we store in the same site. We don't care at this level. When you think about fragmentation, okay. But here you can say, oh, yeah, all fragments are still on the one database. So yeah, you are correct. So that means still, but when we say fragmentation, so maybe we can think like that. First, you fragment it into separate fragments. So then you decide where to put them. So that is right. So breaking it, maybe we can take it as fragmentation, right? So then deciding where to put it, right? We can think of it as studying. Right? I think that might be the idea, right? So here we decide how to break it, right? How to split it in fragmentation. So then you decide where to put it. So that is studying. I think that is why they say related to the service, right? Yeah, maybe two-step process. First, you do the fragmentation, then you decide how are you going to study it. Okay, how are you going to study it? Yeah, okay. So it doesn't necessarily mean that fragmentation is same server, right? No. At fragmentation level thinking, you don't consider about where to save. Then you decide where to save those fragments. So that is stacking. I think that is why I say it's a physical implementation. So this is logically you split it, then you decide physically where do you save it, these fragments. Okay, okay, right. So I think that make more sense. Okay, so it's a two-step process. First do the fragmentation, then do the shredding, because now you all have the fragments. But in reality, practical sense, usually these two must be thought together because you fragment thinking of possible study because that is where you get the advantage, right? Though those are two concepts, in practical designing, you need to think both together because one depends on the other. Okay. So maybe you are doing this fragmentation because you want to put it into a particular site. Okay. But yes, conceptually, you can take it as two things. Okay. I think that makes more sense. Okay. So it's a logical design. So this is how you physically implement, especially the horizontal fragmentation. Okay. So you first break it, then decide when to go. But in reality, you need to think both because this decision may depends on where it's ultimately going. Okay. Right. So you need to think about the location, load balancing, right? Order of access and so on. Right. So auto study means these decisions are taken by your servers depending on the user queries and so on, especially NoSQL databases. The database, because anyway, NoSQL databases are mostly cloud-based, redundancy is there. So then the database decide where to put those things, uh, those partitions, what are the best places or best nodes. Okay. Rather than system administrators decide the strategy. Okay, maybe system administrators decide the fragmentation because that is more logic conceptual thing, but allocation is more performance related thing. So let the DBMS decide because DBMS has better statistic of the performance of uh, executing queries. Actually, databases collect the performance data also. When there's a transaction or query execution, it keep the those performance data, right? So then the database itself can decide uh, maybe these threading related things because it has a better understanding about the performance bottlenecks and so on, right? So that is the idea. Yeah, right. So that is a good question actually. So that kind of questions uh, clarify things, right? Sometimes we just take into granted without thinking too deep, right? Without going into the deep thinking, right? So then the type of data replications can be master slave or peer-to-peer. Anyway, we discussed this in the other topic also. Okay. Uh, so in master slave replication, all writes are done to the master, and master's task is distribute it into slaves, right? So then there's a central failure also, central point of failure, but better consistency because master can handle the propagation in much more controlled manner. Slaves, you can only read, right? You can read. So that is more suitable for read intensive data, right? And less write and more reads, right? Because if because it's less write, you can write it to a master which may not be your closer to you, but you are doing more reads and those are in your local sites. Okay. Yeah, single, these are the disadvantages: single point of failure, right? Replication lag because you always replicate, uh, update the master need to update it, right? And also maybe even you write and read, maybe you don't get what you write because there can be time delay. But uh, if it is the second peer to peer, you update your node. So then if you read, you always get the latest. Now here sometimes you write and you read the same thing and you get the old one. Okay, so that is one disadvantage. Okay. But peer to peer, you update your nearest one or your related one. So therefore, guaranteed when you read, you always get what you write, but not the other nodes. Okay, not the other nodes. So those are pros and cons. Okay. Right. So next, the transparency. So transparency means in IT, transparency means you don't have the visibility. Not having visibility is good. So that means it's handled internal, right? You don't need to worry about it. So if you need to worry about it, that is additional overhead. So therefore, what we need is hide it, right? So here transparency means hide it. Transparency is good thing because hiding means we don't need to worry about that. That means it's handled by the DBMs. Okay. Right. So again, we have different type of transparencies. Location transparency, naming transparency, replication transparency, fragmentation transparency, design transparency, execution transparency, and so on. Right. So location transparency means when you write your queries in a distributed environment, you don't need to specify the site or the location. Right. You don't care. Right. That is called location transparency. But if you refer to it as select all from employee from site one, union select all from employees from site two. So that means there's no location transparency. But ideally it should be just select all from employee. Okay. Without referring to the physical sites. Okay. So naming transparency means uh, there can be different names used internally. Right? Different names used internally. But for you, it's a global naming. Okay. So you use the global common name specified in the global scheme. But in local schema, maybe those are using different names. Okay. But you don't need to worry about it. So then we call it naming transparency. Okay. So replication transparency means there can be replications, but you don't need to worry about that. Right? You don't need to worry about that. You just write your query without considering the replication. Okay? So fragmentation transparency means maybe so horizontally fragmented, vertically fragmented, then you don't need to collect those and join or combine, rather DBMS handling. So that is called fragmentation transparency. Uh, so the design transparency means the users doesn't mean the end users, basically application developers, they don't need to worry about the design of the distributed database. They always work with the global scheme. So once you look at the global schema, you can see something like centralized database. Okay. So the developers, designers, they don't need to worry about your database applications and so on. So execution transparency again, when you are executing a query, complex query, you don't need to specify where to execute the first part, where to do the join. Those things are handled and decided by the distributed database system. So it will decide the best execution uh, strategy, right? So you remember that we get past questions on that, right? So examiner will tell us uh, what is the best execution strategy. But in reality, we don't need to worry about that. Those are handled by the DBMS. But we get question in the exams because we try to understand how the DBMS handle that, right? How the DBMS decide the best query execution path. Okay. Right. So when it comes to query processing, so there are four steps, right? Query mapping, uh, localized query mapping means map your selects SQL statement to relational algebraic level expressions like sigma phi expressions. Right. Anyway, we can take one by one. Okay, we'll take a small break. And after the break, we'll look at the query processing and the optimization. Okay. Right. So first you need to do the mapping of the query into conceptual schema. Okay. So that can be done in the central or controlling side because this is planning stuff. So that must be done in a maybe that nodes itself or maybe in the central side. Okay. So then you need to separate it into nodes. In which node, which processing is done. Okay. Which processing is done. So that is called localization. Okay. So then you can do the global optimization. Uh, that is to reduce the data transfer. So if we that is rather than maybe taking two data sets from here to here, can't we take this data to this and do the join and take it back? Or take this data to there and do the join and take it back. So that kind of decisions you need to take, right? After deciding from which fragments you are going to take, right? Which data, then you need to decide how to do the joins, right? Joins, unions, what is the optimum strategy? Whether you take from A to B and take it, or B to A and take it, or A to here, B to here and take it, and that kind of decisions. Okay. Right. So these are some possibilities, right? A to B and take to C. B to A and take to C. Or take A to C, B to C, and then do the join no whatever. So if you have those are the actually three possibilities. If you have three sites, including the your sites, local site, okay? Right. So this is an example. Those decisions are based on calculations, okay? So those decisions are always based on calculations. You need to calculate how many bytes you are supposed to transfer from A to B or B to A or A to C and B to C. Okay, so then you decide which strategy has the least amount of data transfer because transferring data in network take time. Okay, right. So we can do these kind of things because we are going to do some past paper questions. Okay, therefore I'm not going to do these things. Rather, I will do those as part of the past paper discussions. Okay. Anyway, let's quickly look at this. Uh, so we have the employee table, department table, and we have some field values which are related to the query, the field widths. Okay. So we need to get the first name, last name. So those are in employee table, and then we need the department name, which is in the department table. Right? Department number is the primary key. So therefore, in order to do the join, you need to consider department number as well, because otherwise you can't do the join. Okay. Right. So then what are the strategies? Processing is done only in one table, right? Unless specifically mentioned in the question. Records of entire table is transferred from one from other nodes to the nodes that processing is done. That means no selection, no projection at that place. Okay. So this is for the exam, right? Most of the time, examiner assume that uh, in the in we are doing those processing in one site. So therefore, you don't just extract and take data. You take all the data and one place you do the processing. I think that is to make you the solutions easier, right? So just note it down, okay? After processing, which may include joins, selections, projections, and so on, uh, right? We get the final result, okay? Right. So first we need to convert your requirement into algebraic query, right? Algebraic expression, relational algebraic expression. So this is, you need to do a join between employee and department based on department number. Then project the required three fields, project, selection, projection. Okay. Right. So this is uh, solutions, right, or possible solutions. So number of records in the employee relation, let's assume 10,000. Size of one record in employee relation, 100. Size of the employee relation is therefore 10,000 into 100 byte. Number of records in department, 100, because make a copy of my past paper questions are the say one record is 35, therefore the total size is 3,500. Right now you have those sizes. Now let's look at uh, actually not methods, rather possible strategies. Okay, possible approaches. Right. So let's say transfer employee data and department data into site 3 and then perform the join there. So that means you take this amount of data into site C, this amount of data into site C, and there you do the join. Actually, this may be very costly one. Okay. So that means you need to take this 1 million byte and 3,500 byte from those two sites. Now that's it, because now it's your local processing is need to be done. But this is the total amount of bytes transmitted through networks. So we need to find which one has the lowest. But this is not going to be the lowest, right? Right. So method two, transfer full records of employee to the node 2, that is where department, and do the join and take the results back. Okay, so therefore entire employee records are transferred to other site. So therefore there will be 1 million bytes transferred there. 1 million byte. Okay. So then the query results. So there you execute the query, right? So site 2 you execute the query. So then the result will be uh, 35 into 100. Why? Why? Uh, Sorry, not 35 into 100. Uh, Size of the query results. One record in the result query consists of 15 bytes. This is a resulting result. First name, last name, department name. So that means 15, 15, 10, 40 byte. And we are going to get 10,000 again because there are 10,000 employees. Right? So after join also, we are going to get 10,000 record because we are getting employees. But the width is now 40 byte because the join has already done and selection projections has already done in this site. So therefore now the result is taken to site C. So therefore it's only 40 byte, but still it's 10,000 records. So therefore it is 400,000. So the total is 1,400,000. But uh, earlier it was 1,003,000, right? I think this is worse. Right? This is worse. Yeah, so this is still better than this. Okay. Right. So what about the method three? So there we can take the department details into the employee side, then do the join in the employee side to the first side and take back. So therefore this record set you need to send first 3,035 into 100. Okay. 35 into 100. So that is 3,500. Now you do the join there. So then the result is 10,000 into 40. Right? So that is not going to be different chain because you have 40 byte and 10,000 record. So that is 400,000. So therefore the total is now, so you take now we have the resource in our site C, 3,500 going from B to A, right, 3,500 and 400,000 coming from A to C, and we need the result in C. So the total is 403,000 and 500. So that is the best. That is the best because this is way smaller than the previous two. So therefore, what is the optimum solution? Uh, Take department details to employee, do the processing, and take the result. Okay, take the result. Okay, so therefore, third approach is the best. Okay, so in general, this approach is identify where do we need to have the least data. So take that to the where we need the most amount of data. So then do the join and get the result. Okay, get the result. And in some cases, maybe you have a sigma also. So then the number of records will be even smaller. Right? So that is additional bonus. Okay. Right. So that is when it comes to relational databases. Okay. Relational databases. Now we'll briefly look at if it is NoSQL database, right? How do we do this kind of distributed query handling? Okay, it's not really query, yeah, in a sort of a query, right? No, though it's not a SQL query. Okay. So again, we can do horizontal scalability, scaling, vertical scaling. Okay. So horizontal scaling means adding more and more nodes. Vertical scaling means increase the capacity of uh, each node. Okay. Or we can do both. Okay. Remember, in NoSQL databases, because we more often keep unstructured, semi-structured data, those are not very critical data like financial details, banking. No, these are mostly social media, multimedia, groups, that kind of thing. So therefore, we are happy with eventual consistency. Okay, we are more interested in availability, replication, and eventual consistency rather than dead serious consistency all the time. Okay. Again, you have the master slave versus master master. So I don't know, for some reason they call it master master rather than peer to peer in this node. Okay. But the idea is the same. So master slave, master is responsible for all write operations. Slaves will do all the read operations are done on slaves. Master need to propagate changes to the slaves. So the concept is the same. Okay, concept is the same. Okay. Uh, Updates are propagated to slave nodes, keeping the eventual consistency. Okay, eventual consistency. Okay, right. So the read operations. So usually idea is make all read operations only on slave. Okay. Of course, if you make all read operations also in master, then what is the need of slaves? So therefore, usually this is the approach. Okay. But this doesn't guarantee that you get the latest all the time because there can be time gap between master and transferring it to slaves, right? If you need to, especially when whatever you have written also, maybe you don't get the correct whatever you have written your data because you are also doing the update to the write into the master and it may not have been updated your slave because you read from slave. Okay. Right. So here they use the word master master rather than peer to peer, peer peer. Okay. So that means all the nodes are treated similarly. That means all the nodes are sort of masters. Okay. Reads and write can be performed on any of those nodes. But it is not assured that all reads are done on different nodes, see the same day value. Because, but if you write and read from your node, you will always get at least your data up to date. But there's no guarantee that if you write here and someone read from there, there's no guarantee that they get the latest all the time because it must be propagated. Okay. Right. So again, they talk about the shredding, right? How physically data is distributed. Okay. And again, they can even automate it because these servers have better understanding about statistic about performance of the queries. Okay. We have done past paper questions also, right? That is good. Right. So I'm not going to do these things again because you have the recordings, right? Yeah, we have done past paper questions also. Uh, anyway, let's do it again because this is we are getting closer to the exam. Right. Uh, right. So let's do the 2023 paper two. Don't we have 2024 question? Maybe we have not done 2024 question, right? Only 2023 question, yeah. Right, so let's first do the 2023 because we have the answers also. Then we'll do the 2024 and 2022. Right. So again, you can see that all of a sudden this paper intimidate you or baya right? So the questions are very lengthy, right? You need to do a lot of serious thinking, right? So this paper is not like some other papers, right? They are neither. So these some other papers, they don't actually they are not very serious. Actually, this paper is very serious, or the examiner is also very serious. So this is a very high standard paper actually, right? DBMS data management paper, very high standard paper, right? So in a way, it's good, right? If you are not very serious, sometimes you get frightened, right? Sometimes you mess up it by making mistakes. Sometimes you don't have enough time to read this. Now remember, you need to finish this in 1 hour, right? So how, right? All of the questions. So these are lengthy questions. So if you are not very good at your English, if you're always thinking in your native language, right? So then you are going to suffer. We are going to suffer because that is why we are doing this in English medium from semester one because ultimately you are going to uh, suffer if you do it in your native languages. That is why even all the state universities also now computer science, IT, no, not only that, even science is done in English medium. Right? In universities, they don't use Sinhala anymore. Right? Science faculties, engineering faculties, especially engineering medicine, they don't use any single Sinhala or Tamil word. Okay. So you also need to get into that kind of mindset. Right. So let's do the 2023 paper two. Question 1B. Consider the following database schema of a software company which consists of two relations, project and client. Okay. Project and client. Primary keys are underlined. Foreign keys is in italics. The project and client relations are stored in node 1 and node 2 respectively. The results will be stored in node 3. So that means you expect the result in node 3, right? So project is in node 1. So let's draw it. Node 1. This is node 2. Project is there. And client is in node 2. Client is in node 2. So you need to fight with time. Okay, definitely. Right? Because remember the index questions, you need to do calculations also, right? Here also calculation, but index calculations are, right, more complicated. more time consuming. Right. So this is project details and this is client details. Okay. Note, the client ID in the client relation correspond to the foreign key in project relation. So that means client ID is the, uh, so possibly there is CID. Yeah. CID is a foreign key to do the join. Note, sorry, then relation project contains 3000 records. So here we have 3000 records. Uh, each record is 40 bytes, right? So you need to take it to your world. ඔයාගේ ලෝකෙට ගේන්න ඕන ලියලා තියෙන එක, right? Picture like. Project ID is 10 byte, 10 byte. Project name is 10 byte. Duration is 5 byte. Budget is 5 byte. CID is 10 byte. Relation client contains 1200 records. Each record is 50 bytes. Okay. So then client ID is 10 byte. Client name is 10 byte. Email is 10 byte. Contact number is 10 byte. Location is 10 byte. Okay. So now you can forget about this because everything is there. Okay. 30% of the project have budget greater than 500,000. 30% of the project, 30% of the project has budget less than 500,000. Okay. 30% of the project. Right. So now we have all these details. Consider the distributed query D
So greater
below.
than 500,000.
Yeah, sorry, yeah, greater than 500,000, sorry. Yeah, greater than, yeah, budget. Did I draw it in the other way? Budget greater than 500,000. Okay, I think I don't know. Did I write it other way? Yes, yeah, maybe I wrote it other way, okay?
Yes,
Fine.
sir.
Yeah, so budget must be greater than 500,000 for 30%, okay? Consider the distributed query D below to retrieve name of the project, duration of the project, budget, right? Name, duration, budget. So you need name. Let's use a different thing. You need name. Okay. Right. You need name of the project, uh, duration of the project, budget of the project, sorry, name of the project, duration of the project, yeah, budget, the name of the project clients, right? That is client name of the project clients, and the contact numbers. So you need contact numbers. Uh, of those clients for the project which have a budget greater than 500,000. Yeah, so only those projects we are interested. D, that is your query. You have a sigma. Of course, you need to do the join project and client based on client ID. Uh, then after doing the join, you do the sigma according to this, okay? First you do the join, then you do the sigma filtering for budget greater than 500,000. Then you do the projection of the fields, right? So that is what examiner has given, because sometimes you can do the sigma in the project and do the join. But according to this, first you do the join and then you do the sigma and then you do the phi. Okay. Write three strategies to execute distributed query D and calculate the bytes that need to be transferred for each strategy. But if you go by this approach, right? This approach, so that means you take project details. So there are three approach, right? Take project to the client and do the sigma and file and take the result to site, or take client to the project, do the processing and take the results, or take project to the result inside, clients to the result inside and do this. Okay, but make sure you do it only one place. That is why all these things are combined together. Rather than you take the sigma to the project table, then you need to do processing in two places, right? So that is, examiner has done this to make simpler. Okay. Ah, now we have three approaches. So let's take node 1 details come here, node 2 details taken here, and then do the processing. So in node 1, uh, we need to transfer 3,000 into 40 and 1,200 into 50 bytes. So that is the total transfer, because we are taking those to the side D, right? Node 3. That means 3,000 into 40 plus 1,200 into 50. 3,000 into 40 plus 1,200 into 50. So the total transferred bytes is 108,000 bytes. So that is, take node 1 data to node 3, node 2 data to node 3. Okay. Right. So that is that approach. So what about the strategy 2? Let's say maybe node 1 to node 2 and do the processing and take the result. Okay. Yeah. Node 1 to node 2, take the results here. Okay. Right. So now first you need to take uh, node 1 data to node 2. That is 3,000 into 40. 3,000 into 40. In this question, they have taken only 30% of that data, right? Uh, 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 uh. No, right? No. You take all 120,000, right? Yeah. You take 120,000. Do we take, yeah. So all the data is taken, right? No sigma there, right? No sigma there. All the project data is taken to the client side. So there, that is why final answer also we have the 120,000, right? But now in the site node 2, you can take that records bigger than 500,000. So that means 30% of those. So that means you have only 900 records. 900 records. Now this is happening in node 2. Now, though you get 3,000 record, now you filter out 900 records, right? Because you are going to take, ultimately you are going to get 900 records, right? 900 records. But for those 900 records, now you are doing projection, because now you can take only the relevant fields, because all the processing is here. So for our relevant fields, what we need? We need name, project name, 10 byte, 5 byte, 5 byte, that is 10 plus 5, 15, uh, 20, 30, 40, 50, 60. 60 byte, because you don't even need client ID and project ID, right? So therefore 10, 15, 20, 30, 40, 50. 50 bytes, right? 50 bytes. Uh, So no, 40 byte, why? What do you need? Project name. Yes, you need project name.
So we don't need email.
We don't need, no, we don't need it. But still 10, yes, 10 plus 10, 20, 25, 30, but still 40, 50, right? The client name we
No,
need.
sir.
We need
40. Project name, client name, duration, budget, contact number.
project name you need, duration you need, that is 15, budget you need, that is 20, then client name you need, that is 30, and then you need contact number, yes, 40. Yeah, sorry. 10, 20, 30, 40, yes, 40 bytes. And 40 byte into, right, 40 byte into, you need only 900 records now, right? Because that's sigma is now happened here. So therefore, from here to here, we have 40 bytes. I think there's a mistake here, right? It says 50 byte, right? 40 bytes into 900, right? 40 bytes into 9. I think this diagram is wrong, right? It says 1200 byte, right? Yeah, it should be 40 byte into 900. So there's a mistake here, okay? I will fix that, okay? I will fix that. So it should be only 40 byte into 900. So that is 36,000. So therefore, the total transferring is 120,000 plus 36,000, 156,000. Okay. So let me fix this. Okay. Uh, I have made a mistake there, right? Let me fix it. Otherwise, I will forget it. I will share the updated note as well. Okay. So the calculation is correct, but I have not updated the. Right. So this should be 900 into 40, 40 bytes. Okay. Right. So now it's correct. Right. So that is second strategy, taking node 1 data to node 2, do all the processing and take the results. So now let's move on to the strategy 3. You take node 2 data to node 1, do all the processing and take the results. Okay. But you take all the clients to node 1, right? So we have 1,200 client, 50 bytes. So therefore 1,200 into 50 is taken there. 1,200 into 50, that is 60,000. Okay, so let me take that also here. So this is basically from here to here you go, right? 1,200 into 50. Right, so 1,200 into 50 is taken from node 2 to node 1. Okay, node 2 to node 1, that is 60,000 byte. Okay, so then here you can do the sigma of projects, right? So though you have 3,000 projects, right? 3,000 projects, you can take only 30% of that, right? 30% of that, because ultimately you are getting the project details, right? So therefore, it's 3,000 into 30%, 900, right? So therefore, ultimately you are taking only 900 records. right? 900 records to the node 3, right? Node 3. And total byte is 40 byte because only relevant field. So therefore, it's 36,000 byte. So therefore, total byte transferred is 60,000 plus 36,000, 36,000, 96,000. So this one is also wrong. So this must be, uh, of course, this is total, but now I'm showing is the transfer. Okay. So that is 900 into, right? 900 into 40 is the transfer, right? 900 into 40 is the transfer. Okay. Right. So therefore, it's 1,200 into 50 plus. Okay. 900 into 40 is the total transfer. Okay. Right. So now it's okay. Right. So therefore, now you can decide if you want what is the best strategy also. So this is 96,000. This is 156,000. This is 108,000. So therefore, what the best is the last one. Okay. Best is the last one. Right. So then the C part. Right. So now we have done the A part, B part. Now we are into the C part. So the C part says, consider the student relation given below, blah, blah, blah. This is a different question, right? Yeah, different question. Uh, so the question is, write the fragmentation condition for each fragment using relational algebra expression based on the given data access requirements of each site. Clearly mention the assumptions that you have made, right? Write the fragmentation condition for each fragment using relational algebra expressions based on the given data access requirements of each site. Right? Clearly mention the assumptions that you have made. Right. So let's do that. Consider the student relation given below related to next-gen university. The university is organized into three functional units: administration, engineering, and arts. Okay, so let me take the pen. Right. So consider the student relation given below related to the next-gen university. The university is organized into three functional units: administration, engineering, and arts. The university has set up three computer sites: Site 1, Site 2, and Site 3. Right? Site 1, Site 2, and Site 3. Site 1, Site 2, and Site 3. You can see it's a lengthy question. Uh, one for each functional unit. The data access, that means probably administration, engineering, and arts. Okay. Admin, engineering, art. One for each function unit. The data access requirements vary for each of these sites. It is important to note that administration is not considered as a department. Uh, Administration is not considered as a department, and there are only two departments: engineering and arts. Okay. The student relation is fragmented uh, and replicated in a way to address the data access requirement of the next-gen university. The primary key is underlined. So this is the student relation: student ID, student name, guardian name, contact number, specialization, GPA, department name. Data access requirement. So remember, administration is not a department. Maybe they don't need all the details of the student. Okay, let's see. Site 1 uh, is dedicated to handling university's administrative functions. Yes, administrative functions. This site is primarily responsible for accessing and managing students' personal details. They need the personal details, including their student name, guardian name, and contact number. So they need those, right? Student name, guardian name, and contact number. Okay. But they need to keep the student ID also. Okay. Site 2 and Site 3 are specifically designed for the university's engineering and art departments. Right? So this is engineering, this is art department. First, you need to take the question to your world. Okay. Respectively, these sites are expected to have frequent access to students' enrollment details of their respective departments. This information includes essential attributes such as student ID, of course, student ID both need, specialization, GPA, and department name. Okay, so let's use a different color. So they need uh, student ID, obviously, but why? I don't know why these guys don't need the student ID. And student ID, specialization, GPA, and department name. Okay. This information is included. Uh, this information is include. This information includes essential attributes such as student ID, blah blah blah. Okay, right. Now the question. Write fragmentation condition for each fragment using relational algebra expressions based on the given data access requirements of each site. Clearly mention the assumptions that you have made. So that means you need to write it using relational algebraic expression. Okay. Uh, so basically, you need to do 5 here because it's only one table, right? For the administrative department, it's only 5, no sigma, because they are interested in all the students, right? But you 5 only student name, guardian name, contact name, number. But I will include student ID also. Okay, student ID also, but I don't know if the examiner is interested in student ID. But usually you need student ID as well. So it's just a 5, student ID, student name, guardian name, contact number. Okay, I don't know if the examiner includes student ID. Okay, so let's look at the answer. Site 1, you can see it's 5. Okay, it's a 5. Yes, you can see student ID is taken because you need student ID, right? So then student name, contact number, guardian name. So that's 2 marks. Okay. So then what about uh, site 2? So that is both sigma and phi. First use sigma so that it is department name is engineering, and then you phi for specialization, GPA, department name, and student ID. For site 3, in the sigma you make sure that department name is art, and then phi student ID, specialization, GPA, and department name. Okay, so that is how you are supposed to do, right? So here you can see there's a sigma department name engineering, sigma department name art from student info table, but then you need to do the uh, phi. Where is the phi? What they have done is from student they have done the phi called student info. So then they are using student info. Or you can just combine this part, right? So this you can take this part, you do the sigma and then do the phi. So you can write it like this also. Right? Rather than breaking it. So that means you say sigma department name equal engineering from student table, right? Student table, and then you do the phi of the relevant fields. So that also work. Or you can give this a name, but here they have done the phi first. That is fine, right? Either you do phi first or sigma first. But usually what you do is sigma first. Therefore, I don't like this answer much. So usually you need to do the sigma first and then do the phi. Okay, then you do the phi. But this one looks like first you do the phi and then you do the sigma, right? That is not the usual way. Okay, right. So that is not difficult question, right? So that is fairly easy question. Okay, right. Next, indicate how the original relation would be reconstructed. So that means first you need to, now we have sigma, right? We have sigma, two things. Department name is engineering and department name is art. So that those two you need to union, right? Those two you need to union, okay? Because then only you get all the records. So then you need to connect it with uh, fields saved in the uh, admin. It's admin, right? Yes. Because some other fields are in the admin, right? So then you need to use the common column. The common column is student ID, student ID. So that is why student ID must be in both admin and these two departments. So all three sides, student ID must be there. Okay, right. So let's see the examiner's answer. So you need to do the union, department engineering and department arts. Okay. So you can use those names here, department art, department name. So then you can use the same name here. Okay. Because you have already written the query. I think that is the advantage of breaking your queries into subqueries. So then you can use those names in your this kind of a query, right? So you union the department engineering and department name. Now it's like two tables, though it's the same table. Now it's in two different phases. Once you union, you have one table here, sort of one table. Uh, the personal info is in the other side. So therefore, it's like now two tables you need to join, but based on student ID. That is why personal info table must have student ID. Otherwise, you can't join. Okay. So if it is horizontal fragmentation, you need to do the union to reconstruct. If it is vertical fragmentation, right, vertical fragmentation, you need to join using common field. So that is why when you do vertical fragmentation, we always use a common field. So that common field is primary key. Okay. So is it clear? So it's always good to break down your queries into these names, give them name rather than write the full query so that you can use it in this kind of a reconstruction statements. Okay. Reconstruction statement like student personal info and so on. But I don't like the way they divide this. I will first do the sigma and then we'll do the phi because that is the normal approach. Okay, normal approach. But anyway, both should okay. Okay, right. So it's a very lengthy question. So now we are into the next part. Describe two advantages of distributed database systems. Okay, that is a theory question, right? So that's normal theory question. Still, it's not over. Briefly explain peer-to-peer application and master-slave. Yeah, that is theory. Okay, peer-to-peer and master-slave. Right. So this should be not 2023. One need still not finished, right? So what kind of a question is that? Let me double check the paper. And the examiner give this long question. I don't think. Maybe that is 2022 or 4. By the way, if I get disconnected, I will connect it again, right? Because now there's a power cut here, but I'm running with my backup power. If I disconnect, that means my SLT connection is power bank is over. Then I will connect again using my Mobitel. Okay. Right. So yeah, let's look at the 2023 paper. I suspect, can the question be this long? Yeah, A part, B part, we discussed. Yes, C part, that is what we discuss now. Yes, there's a D part also, right? D part also. But deep, no, no. Now remember, there's a D part, still there's a D part, but anyway, that D part we have already done. That is related to constraint, right? So therefore, now this question must be not 2023 then, right? 2022 or 24. Let's see, 2022. Not that, right? Maybe 2024. This one, right? Branch purchase customer. Yeah. So this is basically 2024 E. Okay, 2024 E. Right. So 2024 we have E. Yeah, only E. Okay, only E. Right. So let's read the question because the answers are, we have already discussed this question anyway, but let's do it again because, right. Consider three question is express the fragmentation condition for each fragment using relational algebraic expression. Okay, right. So let's again, you need to take this question to your world, right? Your world. Consider the three relations related to the shop global reward. Global reads three relations, that is branch, purchase, and customer, which has three branches operated across three locations, Candy, Mother, and Jaffna. The bookstore has set up three computer sites, site 1, site 2, site 3, one for each location. Okay, site 1, site 2, site 3. Site 1, site 2, say site 3. One for each location. The data access requirements vary by site, and the customer and purchase relations are fragmented and replicated to meet the data access requirements of the each site. Customer and purchase relations are fragmented and replicated to meet the data access requirements of each site. Uh, Customer and purchase, right? That is customer and purchase. They don't talk about branches, which are fragmented and replicated, both fragmented and replicated to meet their data access requirement of the each site. The primary keys are underlined and the foreign keys are italicized. Okay, so what are the foreign keys? Branch name, address, contact number, purchase ID, custom ID. Yes, custom ID is there. Hmm. Custom ID, customer name, contact number, address, branch name. Yeah, branch name must be a foreign key, right? Customer ID must be a foreign key. Here, branch name, address, contact number, manager name, no foreign key here. Okay, right. Blah blah blah. Note different locations such as Candy Mathur and Jaffna. Right? Candy Mathur and Jaffna. Yes, Candy Mathur and Jaffna are known as branch names. Those are the branch names. Okay. Data access requirements. So these are three branches. Okay. Data access requirements. Site 1, headquarters in Kandy. So site 1 is Kandy, and that is headquarters. Required full access to all records. Full access to all records in branch relation. In branch relation, full access. And need access to customer and purchase information specifically for Kandy branch. But for customer and purchase, they only need Kandy branch details. But uh, in branch relation, they need full access. So that means maybe the Kandy is both headquarters and it's a branch also. That is why they need customer and purchase information also. Site 2 Mathur, it requires access only to the attributes such as customer ID, customer name. So it must be similar here also. And branch name and customers from Jaffna for Jaffna, customers from Mathur for Mathur. I am just reading parallelly. And need access to purchase information specifically for Mathur branch. Right? Purchase information. Here, purchase information specifically for Jaffna branch. Okay. Right. So now we have read the question. Express the fragmentation condition for each fragment using relational algebraic expression. Okay. Relational algebraic expression. Right. So what about so this should be then Mathur and Jaffna. Okay. Mathur and Jaffna. But this is the head office and a branch. Right. So therefore, for site 1, you need full access to branch, right? Full access to branch. Plus, uh, plus you need to have a fragmentation, horizontal. We are going to have three horizontal fragmentation based on branch name, right? We can call it uh, yeah, customer. Yeah. So that means we can say uh, Candy branch, Mathur branch, and Jaffna branch. So those are sigma of branch, where branch name equal Candy, branch name equal Jaffna, branch name equal uh, Mathur. So that means we are going to have three horizontal segmentation of branch because uh, Candy, actually you don't need Candy branch, right? Because Candy need all the details. Definitely we need Mathur branch and Jaffna branch fragmentation. Okay, Mathur branch and Jaffna branch fragmentation because uh, Mathur keep only Mathur branch related data, Jaffna keep only Jaffna branch related data for branch. Sorry, uh, yeah, yeah, right. Because Mathur must not be given access to the Jaffna and Candy branch details. Jaffna must not be given access to Mathur and Candy branch details. So therefore, maybe you don't need Candy branch because Candy need all the details, all the branch details. Maybe you don't need this. But definitely we need Mathur branch, Jaffna branch. Those are sigma. Okay, those are sigma. Where branch name is Candy, branch name is Jaffna, branch name is Mathur. So then customer ID, customer name, that is this branch name of customers from mother branch. That means you need only those attributes. That means the two branches needs only customer ID, customer name, branch name. That is a 5. But again, sigma branch name is mother, branch name is Jaffna, right? So that is both 5 and sigma for the customer table. So then purchase details, no 5, but it's sigma. So purchase, you need to horizontally fragmented. Purchase mother, purchase uh, Jaffna, but no 5 here. But customer, both 5 and sigma. Both 5 and sigma. Okay. Uh, yeah, that's all right. So we are going to do both horizontal and vertical fragmentation here, but here only horizontal fragmentation. Okay. Branch also we are going to do two horizontal fragmentation, but you don't need to horizontal fragment for candy because candy need all. So those are the fragmentations required, but you need to write it in sigma phi notation. Okay. And so let's see examiner's answers. Uh, so we have the customer info because remember, then we can use that for do sigma because remember we need both sigma and phi. So we can use this customer info to do the sigma then. Okay, sigma then. So customer info, sigma matra, that is matra customer info, sigma Jaffna, that is Jaffna customer info. Okay. Uh, but when it comes to purchase, directly you can do sigma. To can anyway, they have done it for candy also, but I don't know whether you don't need. I don't feel like you need a candy one because candy need all. Anyway, they have done that also. Purchase
It's
candy.
for branch tables. We need all.
Sorry.
We need all for branch table, not purchase table.
Ah, yes, yeah, yeah. So yeah, so the candy need the all details for the branch table. Sorry, yeah. So this is purchase details. So therefore, purchase candy, purchase Matara, and purchase Jaffna. Okay, purchase Jaffna. Uh, but branch details, they have not done any sigma, right? So that means branch details, every table, every branch get the full access. It looks like according to this. You can see they have not done sigma for the branch table. Okay. Maybe because it's just a 3 record table, right? I don't know. For some reason, they have not done any because its question says Matra branch details, Jaffna need Jaffna branch details. So that means you need to do a fragmentation. But here I can't see that kind of fragmentation. Okay. Uh, yeah, I can't see that kind of fragmentation. Examiner has not considered that fragmentation. Maybe because then it's only one record. Right? Maybe that's only one record. But still you can do fragmentation due to security and other reasons. Okay. Uh, right. So this is what the candy branch need. Customer info candy, purchase candy, Matar branch, customer info Matar, that is taken only from this file. Purchase Matar, Jaffna, customer info Jaffna, purchase Jaffna. Right. But they have not considered that concept of candy need access to all the branch details. Matar and Jaffna need only their branch details. That aspect is not addressing this, right? This particular scheme. For some reason, I don't know. But I will do that one also. Uh, Horizontal fragmentation, like candy branch details for candy, sorry, Matara branch details for Matara, Jaffna branch details for Jaffna, and candy, they don't have candy branch details because they don't need access to all. But that aspect is not addressed in this particular answer. Okay, in this particular answer. for some reason, I don't know. Okay. Right. So now we have discussed 2023, we have discussed, yeah, 2023 question we have fully discussed. Okay. I mean the distributed databases. Yeah. 2024, any other thing related to distributed databases? Because now we have done this. Yeah, this is also distributed database related also. Okay. Yeah, that's it, right? So, but let's look at the 2022 paper. Then all three quick papers are covered. Right, so this is 2022 paper. Uh, right, so this is the question. Question 1B. Question 1B. Okay, so that means this is also done. Right. Consider the following relation: employee, branch, and company. Employee, branch, and where is company? Okay, company they have not given. Uh, sorry, in the company database. Sorry, the only two tables, right? Employee and branch in the company database. So therefore, two tables that keeps track of employees and the details of the branches they are working, right? Employees, details, and the details of the branches. The size in bytes allocated to store values of each attribute is listed in the size column, right? In the network, now you can see examiner has given. Now remember, I used to do this kind of a thing, right, for the other two questions, but in this paper, examiner has sort of given this diagram, right? Pictorial diagram. Uh, in a network of three nodes, the relations employee and branch should be stored on node 1. Node 1, you need to keep both employee and, sorry, node 1 and node 2 respectively. That means in node 1, you keep employee details. Node 2, you keep branch details. Okay, branch details. The results are expected to be presented in node 3. Okay, so this should be a calculation question, right? Take here to here, here to here, or here to here, and here to here, or here to here, and here to here. Okay, so it looks like that kind of question. Okay, right. So consider the below given distributed query queue to retrieve the employee's name, NIC, and location of the branch where the employee is working. Right. So you need to join employee and branch based on branch ID. So that you get all the employees and their branch details. But our focus is employee, right? So if employee has 600 records, finally we'll have 600 records. But you are only interested in the employee name, employee NIC, and the location. Location must be coming from branch. Okay. Yeah, location coming from branch, right? So this name must be employee name, right? Because there's no branch name. Okay. There's no branch name. Right. So that is a typical question, right? Typical question. Calculate the total number of bytes to be transferred while executing the query in each of the following strategies. So even they have given the strategies now. Strategy 1, transfer data of employee and branch relation into result sites. That is node 3 and perform the join. So that means 100 into 600 plus 70 into 50. Right? 100 into 600 plus 70 into 50. This much of bytes are transferred. And now the joins and phi happens here. that we don't care because we are interested in data transfer. Okay, is it clear? Right, strategy 2. Employee transfer data in employee relation to node 2 and perform the join operations at node 2. Next, send the result to the node 3. So let's assume not only the join and 5 all are done, right? That is how usually it's done. So that means your employee relations details must be transferred here. Therefore, it will be 100 into 600. That is, first part is 100 into 600. Okay, 100. Yes, 100 into 600. Okay, that is 600, 60,000. Yeah, 60,000. Okay, right. So then here we do the join and then do the file. So therefore, still it will be 100 records. Okay, 100 records, but you will need only these three fields. You will need only these three fields. That is name, NIC, and location. Right? 30, 10, that is 40, and location another 20. So that is 30 plus 10, 40, 40 plus 20, 60. 60 into still 100, right? Because you are getting the 100 records. So 60 into 100, right? Sorry, 60 into 600. Sorry, 600 records. 60 into 600. 60 into 600. Right? So that is the final takeaway. So therefore, it will be 96,000. Okay. Right. So the strategy 3, transfer the data in the branch relation to node 1, perform the join and file, and take the result to node 3. So branch data you are taking to the node 1 now. So therefore, we have 70 into 50. 70 into 50, that is the first part. Right? 70 into 50. This is same as previous, 16 to 600. Because that is your final result after doing joins and everything. That will be 37,050. Okay, 37,050. Right, so that is easy, right? Right, so the next one. Which of the above three strategies can be considered the optimal solution for the district? Now, take the smallest one. This is 37,050, 96,000, 61,000. So last one is the best, right? So because your smallest data set is in the department, so you take that to the other site and do that. So usually that is the best strategy, right? Best strategy. Strategy 3. This since the transfer the minimum amount of data, you need to explain, right? Right. C part. Consider the below given customer relation containing 1,000 rows where cust ID is the primary key, ranging from 1 to 1,000. Okay, 1 to 1,000. Create three fragments of approximately equal size by horizontal fragmentation and state each fragmentation condition using appropriate relational algebra expression. Okay, right. So consider the given customer relation containing 1,000 rows where customer ID is the primary key ranging from 1 to 1,000. Create three fragmentations of approximately equal size. Okay. By horizontal fragmentation. That means you need to break it into horizontal fragmentation. This is a little bit strange question because there's no condition. Just you need to break it into equal size. Okay. That is like 1,000 divided by 3. Okay. 333. And 333. That is maybe 1 to 333, 334 to 666, and 664 to 1,000 because there's no condition here, right? Right? Like location, no department, no such thing. So therefore, we have to go like that. Right? Three fragment approximate equal size by horizontal fragmentation and state each fragmented condition using appropriate relation algebraic. I have no option. I would say 1 to 333, 334 to 666, 664 to 1000. And it's pure sigma. Okay? Pure sigma. Yes, because it's basically size space. Right? So you can expect that kind of question as well. Maybe this is for the performance reason, right? Performance reasons. Right. So second part, customer data. Customer data are distributed over three different locations based on branches, namely Gampaha, Kegol, Kandy. Consider that customer table is divided by location, okay, of each branch where data of the customers belong to the Gampaha branch are stored in fragment C1. Okay, C1. And Kegol branch is stored in fragment C2 and Candy branch is stored in fragment C3. Okay. Write the SQL statement to retrieve the list of all the customers with a balance greater than 100,000 LKR under location transparency. Right. Right. So let's read it again. Customer data are distributed over three different locations, namely Gampa, Kegol, and Candy. Gampa, Kegol, and Candy. Gampa, Kegol, and Candy. Consider that customer table is divided by location of each branch where data of the customers belong to the Gampa branch are stored in fragment C1, K-Goal branch fragment C2, and Candy branch in fragment C3. Write the SQL statement now, right? Not the sigma phi. Read the question. To retrieve the list of all customers with balance greater than 100,000, right? Retrieve all list of all customers uh, under the location transparency. That means you must not refer to location. Right? You must not refer to locations. So already this is horizontally fragmented. So you need to take the union of those, right? The union of C1, C2, C3, but rather than C1, C2, C3, you can say maybe sigma, right? Or can we say C1, C2, C3? No, right? Let's say sigma uh, branch equal candy, branch equal candy, union sigma, branch equal uh, gampaha, union sigma, branch equal actually those are C1, C2, C3, right? Uh, K goal. So now we have all the details, but then balance greater than 1000 LKR. Maybe we can do that also, right? Maybe here we can say and, so maybe afterwards you do the sigma, right? You take the data and then you do balance greater than, balance greater than 100,000. So I will do like that. First do the union so that you have all the data because then we can process it in our side. So then we do the sigma to get the relevant data. Okay. Oh, I don't know if the examiner refer to them as C1, C2, C3, then it is not location transparency, right? So now this is purely you need to write SQL statement, right? Sorry. Right. So that means you can just write normal SQL statement, right? Select all from uh, customer, right? Select all from customer where balance is greater than 100,000, right? So For us, it's a normal query, right? Select all from customer where balance is greater than 100,000. You don't refer to C1, C2, C3, right? So that should be the case, right? Simple SQL query. If, because location transparency. But do we need to refer to the fragmentations? C1, C2, C3, that is my problem. Because C1, C2, C3, the location transparencies, whether it's in the site 1, site 2, site 3. Okay. But C1, C2 are those are fragments, right? Yeah. So one possibility is you just write a normal select statement. So that means everything is transparent. Or you fragment you need to consider, but not the location. But I'm not very, I will write a simple query. But I don't know if the examiner expect that kind of answer, right? Anyway, still I will go for simple select query. Right? Select all from employee where uh, balance greater than 100,000. But I don't know if the examiner go for the C1, C2, 3 and do the union. Okay. I will go for simple select statement. Okay. Examiner has done the union. So that means examiner has expected only location transparency, but no uh, fragmentation transparency. That is I thought. Okay. So you can see it says location transparency. Okay. But examiner has not expected that you assume fragmentation transparency. That means fragmentation is not transparent. You need to handle that. But location is transparent. So therefore, you don't need to worry about the locations or the sites. But still, you need to worry about fragments. So therefore, it's union, right? Yeah. So just keep that in mind, right?
Sir,
Yes.
but he still referred to C1, C2, C3. But how it can be location transparency?
No, I think the C1, C2, C3 are the fragments, right? You can see fragment C1, fragment C2, fragment C. The examiner never referred to them as location, right? So they examiner referred to them as fragments, right? You can see fragment C1, fragment C2, fragment C3. It's not location or site C1, site C2, site C3. So therefore, you need to only consider location transparency, not the fragment transparency. Right. So therefore, that is what I thought earlier. We don't need to consider about the fragment as well. But examiner has considered its location transparent, but not fragment transparent. So therefore, you need to refer to fragments. Right. But again, there's a valid question. So if you refer to the fragment, yeah, no, yes, right. Anyway, this is additional thing, right? Balance greater than 100,000. Yes, you refer to the fragment. So that means candy fragment. Uh, K gold fragment and so on, but this is additional thing, right? Or else you can do these three selects C1, C2, C3, and then you do the where condition at the end after union, right? Where condition at the end, because then you don't here the expectation is you need processing in the site one, sorry, those locations, right? Or the whatever. But if it is location transparency is not there, these things can be handled by server. Though we write like that, uh, right? So here the expectation is insights, these are processed, right? Only relevant data is taken from these three sites, right? That is balance greater than 100,000. And here you do the union. Other approach is you do this where condition after doing the union, right? But then you can't write it as a select statement, right? Because you can't do the union and then say uh, select. So therefore, you need to write it like this in SQL, right? Because in SQL, you can't say do the union and then do the where condition, right? There's no where condition for union. So therefore, you need to write like that, right? But you are referring to the fragments, but you don't refer to the locations. Okay, locations or the sites. I think it's a fair answer. Okay, it's a fair answer. Right. Third part. Write down vertical fragmentation of customer relation, where one fragmentation contains only the information about customer ID and names, whereas the other fragmentation contains customer's branch and account balance. But make sure both has customer ID and it will be a file, right? Because otherwise you can't connect, right? So though it says customer's branch and account balance, I will include customer ID there also. Then it's two file. Okay. You can see both you need to have the customer ID, though examiner doesn't mention, right? Customer ID must be in both. It's just a file, right? Right. So that's a trick. That is a trap, right? So if you don't mention customer ID, you may not get the marks. Okay. Maybe you don't get any marks. Okay. Indicate how the original customer relation could be reconstructed based on the horizontal fragmentation used in C1 and vertical fragmentation used in C3. So then for 5, you need to do the join because now it's like two tables, right? For horizontal fragmentation, you need to do the union, right? For this, you need to do the join. For the previous one, you don't. Here, you need to do the join. That is why you need custom ID. For the previous, you can construct using union. Okay. So for this, you need to do the join. For this, you need to do the union because you have three sides. Union, union again. So idea is vertical fragmentation reconstruction is a join. Horizontal fragmentation reconstruction is unions. Okay, so that is a theory. Right, so that's it. Right, right. So we discuss one more topic today because we are going to stop right now. So possibly Monday, that is tomorrow, right? Yeah, tomorrow evening 7 to 10. We'll do the indexing, right, and possibly do the past papers as well, right? So